Okay, well, it's time for us to do some problems with practice which involves linearization. And that means one thing. You got calculus problems. I feel glad for you, son. We do calculus problems because they are fun. All right, so when you're doing practice, remember, do as much as you can by yourself first. The more you do, the better you get. And when you're watching, make frequent use of that pause button so that you can say, okay, let me see. Oh, let me see if I can do this. Pause it and do it by yourself. The more that you do, the stronger that you'll get. All right, well, let's begin. The first problem, use linearization to estimate the cubed root of 137. Well, we know we're going to do linearization. That's good. But you notice there's some things that are kind of missing here. It says use linearization to estimate this value, but they didn't tell us what the function was, and they didn't tell us what our point of tangency was. Because remember, the linearization is really just a fancy way of saying tangent line. So that means we have to come up with something. So we have to start thinking, what's going on? So let's think about how we would figure out what to do. We know this is our goal, an estimate, which really just means we're going to find some tangent line and figure out where does 137 fit on that tangent line, to the cube root of 137. So we think of, well, what is the cube root of 137? Well, you can even hear it when you say it out loud. The cube root of, see, that says we're doing something to 137. So if we think of it sort of in an abstract sense, if we draw ourselves a little picture here, what's happening here is it sounds like we're taking 137 and we're throwing that into this function called cube root. See, it's the cube root of 137, and that's what we're getting at. So we say, aha, this is our function that we're after. So now we have an idea. All right, so the function we should be using is the function f of x is equal to the cubed root of x. And since we're doing calculus, we'll write that in a calculus-friendly way, x to 1/3. Okay, now we have our function. The next thing to do is figure out, well, where are we doing our linearization at? So we're not doing it at 137. Because if we were doing our linearization at 137, that means we'd have to be able to compute the cube root of 137, and that means the problem would be pointless because we're done. We could already compute the cube root of 137. So how do we figure out where we're at? Well, so what we're looking at is we say we need to be near 137. That's one fact that we need because our approximation is better when we're close. So I don't want to say, oh, let's say, our approximation at 1,000. Well, 137 is not close to 1,000, relatively speaking. Okay, so we want something near 137. But the other thing, so there's two things. It needs to be near. And the second thing is that it needs to be nice for our function. In other words, the cubed root. So how do we find a number that's nice? So what we start saying is, well, we're looking for a number when we take the cubed root of it has a really clean answer. So ideally we should have a number that really is a cube of something. So we think of our cubes, like 1 cubed is 1. That's not even close. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. 5 cubed. Now there's an interesting one. 5 cubed is 125. And notice, 125 is not so far off from 137. I mean, it's not great, but it's not bad. If you went to 6 cubed, for instance, 6 cubed is what, 216? All right, now we're really far off. So among our choices, the one that seems best to take a cubed root of is at 5 cubed, which is 127. So we're going to choose A to be 5 cubed, which is 125. Excuse me, I think I said 127 a second ago, 125. All right, so now we have our plan. We said, okay, because we're after the cubed root of 137, we're going to move over to 125, which has a nice cubed root, and figure out what's happening at that point, and use that to figure out what's happening at 127. Sorry, 137. Oh, my goodness. at least I write the numbers down right. That's something I have going. So let's begin. So our function f of x is x to the 1/3. Our derivative, because we need to figure out our tangent line, 1/3 x, and because we bring the power down, then we subtract 1, 1/3 minus 1 is minus 2/3. And you can think of this as 1/3 x to the 2/3. Okay. Now we need to ask what happens at our point nearby. So when we plug in 125, well, we chose 125 because it was nice. So that's 5 cubed, 125 to the 1/3, which becomes 5. When we plug it into our derivative, what happens? Well, we get 1/3 times 5 cubed to the 2/3. And you'll notice here, the 3 multiplies by the 2/3, that becomes a square. So we really have 5 squared and then a times a 3. So we could write that, that's 25 times 3, that's 75. So now our linearization, it's our tangent line. So we take our value of the function, which is 5, plus the derivative, 1/75 times x minus where our tangent line happened, which is 125. All right, so now we have our linearization. So that's the linearization part. Now we've got to do the use part. So to finish up, we use our linearization in the following way. So we can say that, hey, if I want the cubed root of 137, that's like plugging f into, plugging 137 into our function f, the function that does the cubed root. Well, that is approximately what happens when we plug 137 into our linearization, or in other words, into our tangent line. Okay, so what is that? So that's 5 plus 1/75 times 137 minus 125. Well, if you take 137 and you subtract 125, what do you get? You get 12. Okay, now notice 12 and 25 have a nice common factor. They have a factor of 3 in common. So if you cancel the 3, you really get plus a 4/25. All right, now we could actually go a little bit further and do decimal. Now 25 maybe is not the most convenient thing, but notice 25 is almost like 100. So if you multiply this by 4/4, you get 5 plus 16/100, or 5.16. And there you go. So if you were to take a calculator and do the cube root of 137, you would see it's actually pretty close to 5.16. Not a bad estimate. I don't know what exactly it is. I don't have a calculator with me. But, if I were stuck on a desert island and I had only coconut technology, this would be a great way for me to compute the cube root of 137. Now you might be thinking, I don't think that'd be a top priority if I were stuck on a desert island to go around computing the cube root of numbers. But you never know. And it's nice to be prepared should that day and that need ever arise. All right, so there we go, one problem. Okay, our next problem. So, you have recently started a new job as quality control officer in the new widget factory. Company slogan, you fidget, we widget. A new machine has been installed that takes a rod of length x inches, x is somewhere between 1 and 10, and returns a widget of size x squared plus 3x plus 2. Ideally, you want all your rods to have an output of size 20. Okay, so now we know our target. We want our machine to make an output of size 20. So let's think about what's going on here. We have our widget making machine. All right. So here's our widget machine. And what's happening? Well, you put a little rod in here. of some length that goes into the machine. And out of it comes a widget, which we'll represent as a little bit of a blob here, because I actually don't know what a widget looks like. But okay, so that's the idea. You get some input, something happens, we get an output. Now, you notice here, they have numbers and variables. So if x is our input, then what we do is we look at our function, which takes x squared plus 3x plus 2, and that produces our output. Now, we want our output to be 20, right? Okay, because that's what we want. That's what it tells us. All right, well, how would that happen? That would correspond to starting with a rod of exactly 3 inches. Okay, so good news. If we want an output of 20, we put 3-inch rods in. So we want x to be 3. Perfect, perfect. But you know that the rods are not exactly 3 inches. You know, this is actually a true thing. We think of all these processes as being perfect. Like, I'm going to put in, 10 pounds. Well, you're never going to get 10 pounds exactly. Nothing ever weighs exactly 10 pounds. There's always a little bit of error. And the problem is when you have processes, when you have error in the input, you get an error in the output. And the processes that are complicated, you can have lots of errors, and so you can get this accumulation of error, and that gets you into trouble. So we have to say, okay, we know that our processes aren't perfect. We have to make sure that the errors stay within reasonable bounds. All right, so how do we do that? Well, we want our widgets to be within a half of 20. Okay, so that's good. So that tells us how much wiggle room we have. The output can be 20 plus or minus a half. That's what we have. So the question is, estimate. Okay, now this is a good word. Estimate how much error you can have for the length of the rods that go in. Now, you might at this point notice that we never used the word linearization in this problem. So how do we connect this to linearization? And the answer is, it's this word here. When you see an estimate, what we're really doing is we're going to use linearization. Almost always, especially in this point in our calculus journey, estimates come from saying, well, we have something complicated and we're going to replace it by something simple. Our complicated thing is our function, and our simple thing is a line, which is our linearization. So estimates correspond to linearization. So what's going on here? All right, so what's going on here? So here's our function f of x. What we want to do is we want to say, look, I know how much I can perturb y. I can perturb it by a half. The question is, how much can I perturb x? And I don't have to have it exact, I just have to have it approximate. So the nice thing about this problem is it sounds like a lot of work, but it actually boils down to a very simple idea. And it's the following. In fact, we can start by just sort of saying what's going on. Namely, if I look at the change in y over change in x, that says that's approximately what the tangent line is, the slope, right? Change in y over change in x. So the change in y means how does the function change, the output change? Change in x is how does the input change? So this is a slope technically of a secant line, but when we're close, in other words, we don't move much in our inputs, it's a very good approximation for the slope of our tangent line. So we can say, well, our change in our output, it's approximately the derivative at our point in which we're interested in times our change in our input. So what do we know? Well, we have some pieces. We know what our function f is. We can even write down our derivative. F prime of x would be 2x plus 3. And we can talk about where are we interested. We're interested when our input is 3, right? Because it tells us here. Our ideal situation is an output of 20, which corresponds to an input of 3. So we want to understand what's happening near x equals 3. So we're going to say at our point a equals 3, what do we have? We have that f prime of a is equal to 9. So this part is 9. How much change do we have in our output? Well, this part, we say that's plus or minus a half. So plus or minus a half is approximately 9 times how much change in our input we have. Move the change in input across. So that says that our change in our input, which is how much we are allowed to move our x and our y, how much we are allowed to change our x, is approximately plus or minus 1 over 18. And in our case, our input is measured in inches, so we can say you have to be within 1/18 of an inch. That's how much we're allowed to vary. So we do not have a lot of wiggle room. In essence, the problem in our process is our derivative at 3 is kind of a large number. The larger the value of our derivative, the more sensitive we are to our perturbation of our input. So when we have a large number in our derivative, we're scaling our change in our input by a larger value. If I had a very small number at the derivative, so that would be like the tangent line would have a shallow slope, then perturbing it even by a non-trivial amount doesn't have a very significant impact on the input. And so when we're going through and figuring out what sizes we're willing to tolerate, the answer is we need to stay within about 1/18 of an inch. Okay, good. Well, now we know how to handle widgets. All right. Good. Now, next problem. Find the tangent line to the curve e to the power xy minus 4 plus sine of x minus 1 plus y equals 5 at the point 1, 4. And given that 0.99 comma b is also a point on the curve, estimate the value for b. All right. Now, you might say, hey, how does this have to do with linearization? Well, it says right here, tangent line. See, tangent line is really just linearization. Now, what's the situation here? Well, look at our function. It's not a nice function. Well, I mean, it's not a bad function, but what kind of a function is it? This is an implicit function. In other words, we don't have the ability to solve for y as a function of x for this function. So it's not easy for us to see, well, okay, if we change our input, what happens to our output? That's hard to measure directly. So what can we do? Well, so it's telling us, it says, hey, let's find the tangent line, okay, and then we have, hey, here's something nearby. See, because I want the tangent line at 1, 4, and then I'm just going to slightly perturb the x-coordinate. See, now it's at 0.99. So the question is, what should happen to the y-coordinate? Now, what should be our thought process with this problem? Well, our thought process is something along the following. We have some curve, and I can't know what it does. It's doing something. And all right, so it doesn't even have to look like a normal function. But now I say, here's this point, and it's the point 1, 4. What I can do is I can say, instead of trying to figure out the function and what that's doing, I will find the tangent line to the function, and then I'll say nearby, and this is the important thing about tangent lines, nearby, the tangent line is doing a good job of approximating what's happening. So my implicit function, which is hard to understand, looks like a line near that tangent point. So the idea is now, hey, let's figure out what happens on the line. So whatever happens on the line, it'll be something over here, is going to be pretty close to what's going to happen on the curve. Okay, so that's sort of the thought process. We say, hey, I'm going to have a hard time understanding the function itself, or plugging in 0.99 for x and solving for y, but I can understand what's happening at 1, 4, and I can use that information to approximate what's happening nearby. So we got to find our tangent line. Now, the good news is we already have our point. So, woohoo! Nice. Halfway done. And you can even check that this point does in fact satisfy this relationship, because it would be e to the 0, because it would be 4 minus 4, which is 0. Here you'd have sine of 0. Here you'd have 4. So it becomes 1 plus 0 plus 4 does equal 5. Now, what do we need? Well, we need our slope. So, time for us to take a derivative. And since we're doing implicit differentiation, our sort of thought process when we're taking implicit differentiation is for us to say, and we say, hey, that really should be y is a function of x. All right, so there's our thought process. And so we're going to take the derivative with respect to x, because we like to think of dy dx as being the slope of our tangent line. And whenever we see a y, we always remember, hey, there's really a function of x sitting there. So we begin. Derivative of e to the power xy minus 4. Well, derivative of e to anything is e to that something. And then times the derivative of the upstairs, the exponent. So product rule, derivative of the first times the second plus the first times the derivative of the second. And I'll write y prime as a shorthand for dy dx. The derivative of minus 4 is 0, so we're done with this term. Derivative of sine is cosine. Leave the inside alone, times the derivative of the inside with respect to x, which is 1, plus derivative of y, that's y prime dy dx, equals 0. Now we plug in our point, 1, 4. We could solve for y prime, but that's more work. Evaluate and simplify. Instead of simplify, then evaluate. All right, so we're going to get e to the 0, which is 1. So that's just 1 times 4. 4 plus 1 times y prime, plus cosine of 0. Well, that's 1 times 1 is 1, plus y prime equals 0. So what do we have? Well, we have 4 plus 1 and y prime plus y prime. So we get 5 plus 2 times y prime equals 0. Or we could say 2y prime is negative 5. Or we could say y prime is negative 5 halves. And there we go. There's our slope. Now we have our point, we have our slope, and therefore we can talk about our tangent line. So our tangent line would be what? Well, y minus our y value is equal to our slope, negative 5 halves, times x minus our x value. Or if you were to rewrite it, y would be 4 minus 5 halves times x minus 1. Now this part right here, this is the L of x, the linearization. In other words, in our picture, it's this line here. That's our local line. So now we say, aha, we need to figure out what happens when we plug in x is 0.99. So in other words, where does 0.99 correspond to on this line? So the y value that we're after, b, is going to be approximately what happens when we plug 0.99 into our linearization, which is 4 minus 5 halves times 0.99 minus 1. Well, 0.99 minus 1 is minus 0.01. So that's 4 minus 5 halves times minus 0.01. Well, minus minus makes a plus. Now, you can actually figure this out, because really what do you have? You have 5 halves, which is 2.5. And then times it by 0.01, this becomes 4 plus 0.025. And therefore, we come to the conclusion that our estimate for B should be approximately 4.025. So that's what should happen to our point. And so there we go. That's what's happening. So this comes down to understanding, hey, we're trying to get good approximations to our curves. And when we're looking for good approximations, look for tangent lines. Tangent lines make great approximations. Great. Aha. Good stuff. And so, one last problem. Oh, look at it. Oh, beautiful, beautiful. You and a classmate are preparing to give a presentation in your astronomy class. You know, I think I may have gone into astronomy if I hadn't first discovered my passion for math. All right. Anyways, you have decided that the best way to show how a star gets sucked into a black hole is through a modern interpretive dance, where you will be playing the part of a large blue class O star, and your partner will be the black hole. Oh, you get to play the blue star. Oh, that's nice. You're moving up in the world. Now, you will represent these two astronomical features using paper mache, and you are responsible for making your star. Initially, you were planning to blow up a spherical balloon to a diameter of 16 inches before covering it in paper mache. Now, I'm going to underline this because that sounds like a number, and it's really the first thing that we've come across that sounds very mathy. In fact, I probably should underline the word spherical. Okay, so spherical balloon, diameter 16 inches, before covering in paper mache. But in your excitement, oh, I know how that feels. Whenever you get a good problem, you get a little excited. You ended up blowing the balloon to a diameter of 17 inches. Oh, my goodness. So, what's going on? Well, our balloon was supposed to be like this big, but now it's this big. See, it went a little bit bigger than we needed. So, what's our problem? Well, our problem is we want to use linear approximation. Now, linear approximation is really saying use the linearization. So you see the word linear and approximation. If you put them together, it looks like linearization. Get an estimate. That's another good word. See, whenever you see words like estimate or approximate, you're like, okay, that means I'm using my tangent line as a stand-in for my function. Of how much more surface area the 17-inch balloon has as compared to the 16-inch balloon. In other words, this is going to give you an estimate of how much more paper you'll need to make your model. Because it's a bigger surface, you're going to need more paper. So you have to go make sure you have enough supplies. Now, to help us out, we are told that the surface area of a sphere of radius r is 4 pi r squared. All right, well, that was a lot to digest. But the good news is, oftentimes, when you see problems like this, they can go pretty quick. Really, one of the things we have to learn is to not get bogged down in details. Yes, there's lots of exciting things happening. How will we be doing our modern interpretive dance? What format will it be doing? We don't need to know that. We just say, okay, what does it boil down to? I have a sphere. Then I made it too large. What happened to my surface area? Now, we could have said, look, we can do this exactly, right? Why are we doing the approximation? Well, we practice on things that we can do that are simple so that we know how to do when things are complicated. So, what do we have? Well, our basic formula is that our surface area is 4 pi r squared. Now, let's be careful here. Notice this says radius, that says diameter. What's the difference between radius and diameter? Well, radius, if you think of a sphere, well, the radius of the sphere is from the center out to the edge, right? This is our radius. The diameter of the sphere would go from one end to the other end. So if you're thinking about it in terms of a sphere, so for example, you can say start at the North Pole and go to the South Pole. So from pole to pole, that's the diameter. You go all the way from one end to the other. Okay, so the relationship is that diameter is twice the radius. So what happened? Well, we wanted r equals 8. We got r equals 8.5. And so you could say that our change in our radius was 1/2 inch. That's how much our radius changed. Now, where does linearization come in? Well, it's the flavor of linearization that says, how much does one variable change when I change another variable? And the basic philosophy would say, well, let's call this our function f of r for shorthand. Our change in our output, which is surface area, would be approximately the derivative of our surface area at some desired point times our change in our input. Now, we are after this, the change in our surface area, and in particular an estimation. Well, this is good because this is an estimation. We know what our change in our radius is. It's 0.5 or 1/2. So we need to figure out what's our derivative. Well, if our function is 4 pi r squared, our derivative would be 8 pi r. Now, what point are we interested in? Well, we go based off of where we wanted to go. That was sort of our ideal situation. That's what we should have done. So f prime of 8 would be 8 pi times 8, which is 64 pi. Yes? Yeah, it is. All right, good. So we put this together, and we say that the change in our surface area is approximately our 64 pi. That's what happens, that derivative at 8 times our change in our radius, which is 0.5. And if you multiply that together, you end up with 32 pi. Now, pi, it's about 3.14159, right? Because there's that classic chant. You know, cosine, secant, tangent, sine, 3.14159. Woo! Yeah? Yeah, of course, we all know that chant. Okay, so if you times 32 times pi, you're really close to about 100. So it's in the ballpark of 100 square inches. Now, to give you some sort of sense of how much that is, it's about a little bit more than what you see on a piece of 8.5 by 11 inch piece of paper. So you need about a little bit more than that. So, all right, well, that's our estimate, and there we are. And that's actually our last problem. What a fun set of problems. All right. Well, thank you for coming. Hope you're enjoying your practice. Make sure you keep it up. You're getting better. I know it's hard to feel it from day to day. It doesn't really feel like you get better. But when you start looking at week to week or month to month, you're like, wow, I'm getting great. Of course you are. So keep it up and have a good day.